Welcome. In this lesson, we're going to look at tangent planes and differentials. Let's start with tangent planes and normal lines. If R is a smooth curve on the level surface F, and F is a differentiable function, then f of GHK is equal to the constant C. If we differentiate both sides, then our right-hand side is equal to 0. Now, differentiating the left-hand side, we get the partial derivative of f with respect to x times dx dt plus the partial derivative of g with respect to y times dy dt. There's the chain rule in these two sections. And then the partial plus the partial derivative of k with respect to z, chain rule, times the derivative of z with respect to t. And there's our left-hand side, and that's equal to 0. Here we can see that the left-hand side is the product, or dot product, of the gradient vector of f and the velocity vector, dr dt. At every point along this curve, the gradient is orthogonal to the curve's velocity vector. Here is a visual of our gradient vector, which is orthogonal to the velocity vectors on the smooth curve. And I've drawn this point here, P naught. All velocity vectors at P naught are orthogonal to the gradient vector at P naught. So the curve's tangent lines all lie in the plane through P naught, normal to the gradient vector. Let's look at the definition of the tangent plane at a point. The tangent plane at the point P naught on the level surface f of x, y, z, which is equal to a constant, and f is a differentiable function, is the plane through P naught normal to the gradient at P naught. So this is the definition of the tangent plane. So the tangent plane to f at P naught is this equation. The partial derivative of f at P naught times x minus x naught plus the partial derivative of the function f with respect to y at P naught times y minus y naught plus the partial derivative with respect to z of f at P naught times z minus z naught equals 0. And the normal line to f equal to c at P naught is x equal to x naught plus the partial derivative of f with respect to x at P naught times t. Y is equal to y naught plus the partial derivative of f with respect to y at P naught times t. And z equals z naught plus the partial derivative of f with respect to z at P naught times t. Let's try an example of finding the tangent plane and the normal line of a surface. Find a tangent plane and normal line of the following surface right here. At the point P naught. First, let's find the gradient at P naught. So we take the derivative or the partial derivative of f with respect to x in the I direction plus the partial derivative of f with respect to y in the j direction plus the partial derivative of f with respect to z in the k direction, all at the point P. And this gives us 2I plus 4j plus k. This means that the tangent plane is 2 times x minus 1 plus 4 times y minus 2 plus 1 times z minus 4, and this is all set equal to 0. Or we can write this simply as 2x minus 2 plus 4y minus 8 plus z minus 4 equals 0. And to simplify this, we have 2x plus 4y plus z is equal to 14. I move the constants to the right. Let's move this up. So this represents our tangent plane. Now we find the normal line, and that is x is equal to 1 plus 2t, y is equal to 2 plus 4t, and z is equal to 4 plus t. And this is our normal line, or the line that's normal to the surface at, let's move this down here, P. So when we found the tangent line here, we used our formula for the first part, which is the partial derivative of f with respect to x at P naught times x minus x naught. That's our first term right there, plus the partial derivative of f with respect to y times at P naught times y minus y naught, and that's our second term that we have right here, the 4 times y minus 2, plus the partial derivative of f with respect to z at P naught times z minus z naught, and there's our last term right there, and that's 1 times z minus 4, and that's all set equal to 0. So let's put equals 0. So that's our first formula for finding the tangent line, and then we have our formula for finding the line normal to the surface, which is x is equal to x naught plus the first derivative, or excuse me, the partial derivative of f with respect to x at P naught times t. Let's fix our f. And our second equation is y is equal to y naught plus the partial derivative of f with respect to y at P naught times t. And then our last equation is z is equal to z naught, that's from our point P naught, plus the partial derivative of f with respect to z at P naught times t. To find an equation for the plane tangent to the smooth curve z, which is equal to a function of x and y, at a point P naught, where z naught is equal to f of x naught y naught, we start by looking at the equation z is equal to f of xy. This can be transformed to f of xy minus z equals 0. This means that the surface z equal to f of xy is the zero level surface of the function f of xy such that it is equal to f of xyz such that it is equal to f of xy minus z. So let's take the partial derivative of big F. The partial derivative of big F with respect to x is the partial derivative with respect to x of little f of x, y minus z, which is equal to the partial derivative of little f with respect to x minus 0, and therefore equal to the partial derivative of little f of x. Let's move that up. That's coming up in sections. We'll fix that. Okay. So now we want to know what is the partial derivative of big F with respect to y, and that's going to be the partial derivative with respect to y of f of xy minus z. You can probably see where I'm going with this. That's equal to the partial derivative of little f with respect to y minus 0, which is the partial derivative of little f with respect to y. And probably you can imagine what the next one will be, that the partial derivative of big F with respect to z is equal to the partial derivative with respect to z of f of xy. Now there's no z in this one. Minus z. There's no z in our function f of xy. So that's going to be equal to 0 minus 1, or negative 1. So using the formula for the plane tangent to the level surface at P0 reduces to the following. The partial derivative with respect to x of f at x0, y0 times x minus x0 plus the partial derivative of f with respect to y at x0, y0 times y minus y0 minus z minus z0, which is equal to 0. So let's summarize this on our next slide. So the plane tangent to the surface z, which is a function of x and y, at the point x0, y0, z0, which would be f of x0, y0, is the partial derivative of f with respect to x at x0, y0 times x minus x0 plus the partial derivative of of f with respect to y at x0, y0 times y minus y0 minus z minus z0, all equal to 0. Let's move this up here. Let's try an example with this. All right, here's an example. Find the plane tangent to the surface z equal to x cosine y minus y e to the x at the point 0, 0, 0. So let's start by calculating the partial derivative of f with respect to x at 0, 0, given that f of xy is equal to x cosine y minus y e to the x. So let's move this up here. We'll put that over there. And let's find our partial derivative of f with respect to x. And that's going to be cosine y minus y times e to the x. And again, we're evaluating this at the point 0, 0. So we have the cosine of 0 is 1 minus y times e to the x, and y is 0, and e to the x is 1. So this is going to give us an answer of 1. So let's move this up. It's not quite fitting, so we'll put it here. And that's a 0, 0 there. It's a little hard to see. I don't know if I can fix that. Okay, so now let's find the partial derivative of f with respect to y at 0, 0. And let's see, that's going to be equal to x times, the derivative of the cosine is negative sign, so negative x sine y minus e to the x. And again, this has to be evaluated. I'll write this one neater at 0, 0. Well, the sine of 0 is 0, so this is going to be 0. Minus e to the 0 is 1, so this comes out to be a negative 1. And let's move this one up. So using our equation for the tangent plane, we end up with the partial derivative of f with respect to x, which is 1, times x minus x naught, which is x minus 0, minus 1 times y minus y naught, which is 0, minus z minus z naught, which is 0. And this is all equal to 0. So let's simplify this, and we get 1 times x, which is x, minus y minus z is equal to 0. So this is the equation for our tangent plane. Let's try another example. Here we have this surface f of xyz, which is equal to x squared plus y squared minus 2, which is equal to the constant 0. So this is our surface. And we have a second surface, g of xyz, which is equal to x plus z minus 4, which is equal to 0. These two surfaces meet in an ellipse. So we're going to find the parametric equation for the tangent line 2e at the point P naught, which is 1, 1, 3, where E is our ellipse. I've drawn a picture here where this is our ellipse, and what we have here is this cylinder is formed by the x squared plus y squared minus 2 equals 0. And here I've drawn in our x-axis, our y-axis, and our z-axis. And then the plane we have here, a little arrow, this plane right here, comes from the equation x plus z minus 4 equals 0. So we're looking at where this plane intersects this cylinder, and what we do is we get this ellipse. So in green here I have the point 1, 1, 3, P naught, and here's the gradient vector of G in purple. Let's see, I'll color code it here, gradient of G. And now let's change colors. I'll do the next one in green. And then what we have is the gradient of F, which is perpendicular to the cylinder. We'll have that come out this way. That's in green. So that's the gradient of F. And now, in light blue, I have the cross product of the gradient of F with the gradient of G. I color-coded them to make them easier to, because I couldn't squeeze in the next to the vectors, their labels. So let's start by finding the gradient of f at the point 1, 1, 3. I'll say P naught, we know that's 1, 1, 3, and that's going to be equal to 2x in the I direction plus 2y in the j direction. Again, that's at our point 1, 1, 3, so that's going to be 2 in the I direction plus 2 in the j direction. And let's move that up. That's our gradient of f. And now we're going to find the gradient of g. Again, this is at our point P naught, and that's going to be I plus k, and that is at the point 1, 1, 3, so of course it stays as I plus k. I'll move that up. So those are our two gradients. And what we want to do here is we want to find the vector v, which is going to be the cross product of the gradient vector f and the gradient vector g. So that's going to be the cross product of 2i plus 2j, that's crossed with ik. And that's going to give us, well, a matrix or a determinant, ijk here. And we have a 2, and a 0, and then we have a 1, 0, 1. And when we evaluate this, we can use diagonals. We get 2i minus 2j minus 2k. Now let's move that up here. So this 2i minus 2j minus 2k is the equation for the cross product of f, gradient of f and the gradient of g, which is our blue line right here, and it is perpendicular to the gradient of g and the gradient vector f. And from this we get our tangent line, which is in parametric form. X is equal to 1 plus 2t, y is equal to 1 minus 2t, and z is equal to 3 minus 2t, giving us the parametric equation for the tangent line.